Welcome to this tutorial video. Today we'll be looking at the power transmission system. It's studied in Unit 3 VCE Physics. A basic transmission system has the following components. Traditionally there's a generator of some sort. Next door to the generator we have a step-up transformer which pushes the voltage up. We then have a distribution system in terms of a transmission line. Quite often that's many hundreds of kilometers long, so this isn't drawn to scale. We then have a step-down transformer before our voltage and power reaches the device or destination. Traditionally, the generator would be given as a power of kilowatts or megawatts, and from that you can calculate the voltage from the currents or the current from the voltage. That's important because we have the voltage coming from the generator, that then enters the primary side of the transformer. The current also from the generator is the current in the transformer's primary coil. The transformer follows all the traditional rules in terms of the ratios of turns, volts and amps. And then at the end, the current coming out of the secondary side of the transformer, step-up transformer, is the current that travels all the way through our transmission lines. The voltage, however, when it leaves the transformer of the secondary side of transformer A, it's the voltage that starts across the distribution system or the transmission lines. As we'll look later, we'll see that there is actually a voltage drop. It's not as though the voltage coming out of the secondary of transformer A is the voltage in the primary of transformer B. Unfortunately, we have voltage drop. Let's now look at that. The voltage drop in the transmission lines is equal to the current times the resistance of the lines, and the power loss, importantly, in the transmission lines is equal to I squared R. Note that the voltage at the end of this transmission line will be equal to what we had coming out of the secondary voltage of transformer A, the step-up transformer, minus the V drop, whatever I times R within the transmission lines are. And we'll look at this in an example shortly. Then we reach the transformer B, the step-down transformer. So the voltage at the end of the transmission here is equal to the voltage in the primary coil of the step-down transformer, and of course the current in the transmission lines is that of the transformer in the primary as well. So the current coming out of transformer A in the secondary is equal to the current in transformer B in the primary. Now the output voltage of the transformer or the secondary voltage is equal to the voltage the device receives, as is the current coming out of the secondary turn or the secondary coil of the transformer. It is the current the device reaches, and as always the ratios for turns, volts and amps holds true as well. So let's look at an example. First of all, the device. The device can use all the traditional P equals VI and V equals IR equations to be able to make calculations as well. Now for an example. So a diesel power portable DC generator is used to power lights on a light tower at an isolated football ground. The generator produces a constant, here's our generator, 500 volts DC. Generator is approximately 500 meters from the light tower, and the two wire transmission lines connect the generator to the light. Each of the wires in the transmission lines has a resistance of 5 ohms. So collectively the transmission lines has a total resistance of 10. It's really important, sometimes examiners will try and trick you with the statement. Here it says each of the wires has a transmission of resistance of 5 ohms. Sometimes they say the total transmission resistance is. Ignore the resistance of the other connecting wires. The system is shown below. With the light on, the generator has an output of 20 amps. So, same question. Question 1, what's the power output of the generator? Okay, we know the generator has 500 volts being produced, and we know that there's 20 amps, and we're after the power of the generator. So traditionally P equals VI, the standard equation, 500 times 20 gives us 10,000 watts. Question number 2, what's the power loss, the total power loss in the transmission lines? Well, power loss is a question mark. The total resistance is 10 ohms, and the current traveling through the transmission lines is 20 amps. We know that power loss is I squared R. 20 squared is 400 times 10 is 4,000 watts for our power loss. Question 3, what's the voltage or potential difference across the terminals PQ? So this is way up here after it's transmitted through the lines and we receive it at the lights. So that's what we're trying to work out. The voltage at PQ. The voltage of the generator is 500 volts. Now, there's a resistance, a total resistance in the transmission lines of 10 ohms collectively, and a current of 20 amps as we can read there. So the voltage at point PQ is equal to the generator's voltage minus the voltage drop in the transmission line. So we start at 500 and then we subtract the I times R of the transmission, which is 20 amps by 10 ohms, gives us a total of a voltage drop of 200. 500 take 200 is 300 volts. So we're starting with 500 and we're only reaching our light tower with 300 volts remaining. Quite a low efficiency. So the football players find the lights too dim. They call in an electrician and she suggests the following. Retain the diesel motor and replace the DC generator with an AC alternator producing 500 volts RMS. Insert a 1 to 10 step-up transformer between the alternator and the power lines and a 10 to 1 step-down transformer between the power lines and the light tower. Now the transformers can be considered ideal and the arrangement is shown below. The lights are on. The resistance of each wire of the transmission line is still 5 ohms each. Ignore the resistance of the other connecting wires, and again the output of the alternator is 20 amps RMS. So what would be the RMS voltage or potential difference now at the input of the transmission line? So we want to know, we're starting here, we want to know what is the voltage between point X and Y. Well, we can see here we're using a step-up transformer, so the voltage should increase. Let's look at the maths. At the step-up transformer, the number of turns in the primary to secondary is a 1 to 10 ratio. The voltage in the primary side is that of the alternator, which is 500 volts, and we want to know really what is the voltage on the secondary coil side, voltage between X and Y. We actually know that goes from 1 to 10 terms, so it's going to be times 10. 500 times 10 will give us 5,000 volts with common sense. But mathematically, the ratio of the volts from the secondary to the primary is that of the number of turns from the secondary to the primary. We can multiply our VP across to the right-hand side of the equal sign and create a new equation. Substitute in our numbers. 500 times 10 gives me 5,000 volts. Question 5. The primary of the step-down transformer has 4,800 turns. How many turns are in the secondary winding? Now, if you recall, this was a 1 to 10 ratio. A 10 to 1, my mistake. 10 turns in the first drops down to 1 in the second. So the number of turns in the primary is 10, the number of turns in the secondary is 1. Our primary turns, we had 48,000. I don't think that's right. It was 4,800, my typo, sorry. And we want to work out what is the number of turns in the secondary. So again, the number of turns in the secondary to the primary is a 1 to 10. So it drops down by a factor of 10 because it is in fact a step-down transformer. So it will have 480 turns. My mistake for putting in 48,000 turns. It can be a bit misguiding. Question 6, what's the power loss in the transmission lines? So if we have a look, within the transmission lines, we've got a current of 2 amps because we started here with a current of 20 amps. And whilst the voltage is stepped up 1 to 10, the current drops by a factor of 10 because the power in the primary must equal the power in the secondary. So voltage goes from 500 to 5,000, the current goes from 20 dropping down to 2. So the current in the transmission line will be 2 amps, and we know the total resistance is 10 ohms. P loss is I squared R. 2 squared is 4 times 10 is 40 watts. A lot less power loss when we use these transformers. And that's the whole objective of stepping up then stepping down for transmission. Finally, what will be the voltage at the output of the step-down transformer? And that means up here at the output getting to PQ. Remember last time? Of the 500 volts, we only had 300 remaining because 200 was lost. Let's now have a look, please, at what effect these transformers have. So at the secondary transformer, or the step-up transformer, we see the number of turns in the primary to secondary is a 10 to 1. It's stepping down by a factor of 10. The voltage going into the primary coil, it was 5,000 here, but it's lost that voltage drop of IR, which was 2 amps times 10, so it's lost 20 volts. So by the time that 5,000 volts from the first transformer in the secondary coil reaches the second transformer, the step-up transformer in the primary coil, it's lost 20 volts, so it's down to 4,980 volts. It then has a step down of 10 to 1, so the voltage being received at the secondary coil of the step-down transformer will be 1/10 of that. Mathematically, we write this out. We can see that the ratio of voltage of secondary to primary would be that equal to the number of turns secondary to primary. So we multiply across the VP to the right-hand side of the equals, and we have VS equals VP over NS over NP. Put in our numbers, we're dividing by 10, and the voltage becomes 498 received. a lot better than the first arrangement without transformers that had a voltage drop of some 200 volts and received only 300 volts at the output. I hope these examples have helped. Try and explain the system. Remember, we always have some kind of generator, a step-up transformer, transmission lines, a step-down transformer, and then some device or destination. I hope that's helped. Work through examples, use practice exams, and study hard. Thanks for watching.